Hello, this is Matt Smeal and Sue Lin. We're going to be covering our project on DC to DC converters for rotating renewables for power electronics.
So this is the overview of our presentation. We have the project abstract, introduction and background, project objectives, the design and methodology, timeline, further work and lessons learned, and then conclusion and references. So for the abstract, presence DC to DC boost converter design for more efficient power extraction of low-speed rotation renewables. Focused on application to a senior design project, hydrokinetic turbine or HKT with a 350-watt DC generator. This requires 2,700 RPM for 24-volt output, but even with generating speed from fluid flow, it will not reach this speed. A DC to DC step up is needed to allow connection to batteries/charge controllers. A basic design, simulation, and further recommendations are discussed accordingly. Renewables, both grid scale and distributed energy resources, or DER, are becoming more prevalent. Similar to horizontal wind turbines, group member Matt Smeal, his EE senior design project was on slow water HKTs for electric generation. The Yitech 24-volt 2,700 RPM motor was selected to be run as a brushed DC generator for the project demonstration. Designed for operation at 1 foot per second water flow, warranting relatively slow rotation speeds. At low RPM means low voltage, so a DC to DC generator is necessary. This will allow for continuous energy extraction even at minimum or non-ideal water flow. For the project objectives, we have layout and present basic calculations for a DC to DC boost converter 1 to 12 volts. Select devices in simulation software, which we use in our multisim, and run a steady state simulation. Find an operation range for the device and complete this within 1 month timeline of the semester that we have. So the main methodology / design approach for this was reverse engineering from the specifications. Our specifications that we selected was 1 foot per second per minute, water flow for HKT, blade rotation speed at 30 RPMs, gearbox ratio, so generator shaft speed is 120 RPM, relatively constant speed, but the torque changes. Linear approximation of voltage output at 120 RPMs, 1.067 volts. Nominal converter output, 12 volts, 90% power conversion efficiency, 10% tolerance in input voltage to maintain 12 volts, allowable ripple of 600 millivolts, and max load current, 300 amps. Average DC current should be no more than this. And then this is the block diagram that we use, and it shows where we want to put a microcontroller for feedback. And this is the design that we end up using.
So our general approach again, we made some assumptions regarding the input. Because it's a DC generator, there's going to be some commutation from the commutator. So we just assumed that there was an LC input filter, so there wasn't any ripple. Ideal controller switching and pulse width modulation as well. And then we also just did this for a standalone device. You'd probably want to do this for maybe multiple of these turbines if that was, in an array or something like that, in which case you change the duty cycle and everything. So for the design phase, we did standard calculations. We selected commercial components that were available on National Instruments Multisim version 14. And then we just laid out the circuit and ran a steady state circuit analysis for the simulation phase. So the working principles, the general function of a DC-DC step-up or boost converter You basically open and close an electronic switch. It could be a thyristor, silicon control rectifier, any of those things, a transistor, whatever it might be. We just used a model transistor with diode for our simulation, but you could use any. So the biggest thing is the output voltage, depending on the duty ratio, is either going to be greater than or equal to the input voltage. And again, you control that by that duty ratio, so on time versus off time for the DC. A larger duty cycle means a larger output voltage. So and obviously that's controlled by PWM for a given frequency, and we'll show which we selected after that. But you can see the circuit over on the right. You've got a diode, fixed inductance and capacitance, and then a variable load resistor as well. So general things that we went through. So we first calculated the duty cycle that we wanted for 1 to 12 volts. So that is, and we also factored in, of course, the diode voltage drop. We assumed 0.7 volts. So you can see 12.7 in the denominator there for that calculation over on the top left. That got us 0.916 for our duty ratio. And obviously that can change with the input voltage. That's where we want to have a controller that would try and vary the duty cycle to match that and keep that duty cycle constant. So there's also a correction factor that we used. We didn't really have to change anything after that, but it's for like real inductors, which we did choose to do just because for boost inverters, that's actually important. So the resistance of your inductor actually matters. So we factored that in. And our calculations for minimum gave us 1.62 microhenries, and we rounded that up for making sure we had continuous current operation, meaning it doesn't ever go to 0 amps. Of about 2.025 microhenries. Then we calculated the minimum capacitance from the ripple that we had specified, and that gave us roughly 0.91 microfarads, and we just rounded that up to 1 microfarad. And you can see in blue the ones that we selected. So Borns is the manufacturer of our 2 microhenry. That's what we selected, 2 microhenries for the inductor, and then 1 microfarad for our capacitor. And you can see the actual inductance here that we measured, or resistance, excuse me, that we factored back into this correction factor. And then for the capacitor, we really didn't worry about the ESR in this case. Over here, you can see this was sort of a concern considering how high our duty cycle is. But as the duty cycle goes up for a non-ideal case with this correction factor, the efficiency tends to drop. So our initial circuit that we designed in Multisim actually had some voltage spikes, which is probably from the switching and just the storages in the inductor. So to fix that, we actually added this little, I've named it C snub, but it's like a snubber capacitor. It's a pretty small capacitor, just added in parallel, and that helps smooth out, as you can see, the ripple here. In reality, you probably want to do like a snubber circuit for the switching and this diode over here. So for our actual simulation, this is actually the load variations. It's still pretty decent efficiency, even with variations in load, more ripple, unfortunately. But for our standard situation with 100 ohms, it meets all the criteria pretty much. So 99% efficiency, probably just because it's such low current. The ripple is perfectly fine. You can see this over here. The only issue, as you can see over on the right, is the startup transient. It's really, really high. So we probably need a snubber circuit or some kind of diode to protect that. It's almost double the 12-volt output that we want over here at the beginning. So for further evaluation and performance, these are the lower load resistances shown over here. This is 50 and 10 ohms. And you can see some pretty major spikes. Definitely need a controller to help deal with the switching frequency. We selected 200 kilohertz. Just that's something that the textbook that we used, a lot of those designs that you saw and a lot of those equations and circuit diagrams that came from the textbook from Daniels. It's in our references. They recommended using that just because the higher frequency means you can minimize the inductance and capacitance values that you need to get, which helps with pricing and things like that, commercially available devices. Over here on the left, I think actually we were starting to see the effects as you zoom out of possibly impedance matching because it's 200 kilohertz. or sorry, excuse me, impedance mismatch. But I'm not too sure about that. We'd have to look into that. For the variations of the input voltage we wanted to test for, a controller is definitely needed to vary the duty cycle. Without it, that voltage ripple goes up pretty significantly, as you can see. So that's definitely something we want to deal with. At the lower end, it's not too bad, about 0.626. It's still near our range of 600 millivolts. But when you go up to the upper end, it's quite bad. It's about 4 volts, so it doesn't look very good. So that definitely needs to be taken care of with varying either frequency and or duty cycle, depending on the load and depending on the input voltage. Here is our project Gantt chart. So again, we planned for about a month in April. So starting with the research for DC-DC converters, we went through the textbook to learn about just sort of the design process, how they work, and also looked on some external sources online. And then a lot of the research also was, excuse me, part of my senior design for hydrokinetic turbines and just sort of the torque speed and voltage characteristics of DC generators and things like that to help us, sort of prep for the beginning end of that. And then we did the multi-sim circuit. That didn't take too long. There was a lot of work to fix that sort of spiking at the beginning. So we just chose the simplest one, which is a parallel capacitor. A snubber circuit would definitely be best. So for further work, there's a lot to be done here. There's several additions that are needed for like an actual final design for this application. For one, we need a microcontroller for feedback control. So you want to drive that output voltage error to 0, so you want to keep it at 12 ideally. And it could do that by varying the frequency if there's a load change, because you remember L and C are fixed. We have fixed values for those devices. Or it could vary for the case of input voltage variations. Maybe the speed does change a little bit. We would want to vary the duty cycle, which we do in that PWM. At 200 kilohertz, again, there might be some concern for impedance matching as well, or reflections. So that'd be something we'd have to analyze. Again, the snubber circuit, very important for the transient over voltages we saw and the storages at the beginning. We may actually want to get it up to, its steady state operation before it gets connected. I'm not too sure. Another thing we have to ensure is that the real diode storage elements in the switch, they're all rated for the steady and transient voltages, and make sure that they don't, exceed those ratings. And then also, this would probably help with efficiency, considering like an array of devices and how they would connect to like a battery or charge controller. If we had few of these turbines, let's say 6, then you have 6 volts roughly, and that duty cycle can be dropped and the efficiency can be improved as well. So for our conclusion, the preliminary design is effective for that 100 ohm initial case and for the starting duty cycle and frequency. Those low current specifications aren't necessary. We didn't even get near 3 amps. But if you had multiple devices, that might be good to keep in mind. As for the load resistance and the input voltages, though, changed, the design fails without any control system. So it's got to have a control system. I think in general for the project, utilizing a low-speed AC generator would be best, and then just doing AC to DC conversion, and then do the DC-DC conversion process after that before you go to another inverter. I personally think that would be the best choice, just so we can avoid the issue of gearing and things like that. And yeah, here are the references that we use for our project. If there's any questions whatsoever, you can contact Sue or I. And thank you.